welcome to the fourth part of Unit 10. And as promised, in this portion, we are going to make the connection between our two concepts of work and energy. So what does work do? Work adds or removes energy due to non-conservative forces. Oh, so that's a horrible definition. And part of the reason that it's horrible is because we now have to address what does it mean for something to be a non-conservative force. Well, let's start this conversation by listing conservative forces versus non-conservative forces. Okay, conservative forces, you will encounter two of them. One is the gravitational force, and the other one is the elastic force, or the force due to a spring that follows Hooke's law. Okay. What's a non-conservative force? Pretty much anything else. Okay, there is at least one exception to this one, but it doesn't come up until next semester, Physics 202. So we're going to stick with this list for the moment. Okay, what's the difference between a conservative force and a non-conservative force? To me, the big difference is when the motion of the object changes direction, does the direction of the force change? So if you think about gravity, the gravitational force always points downward. Regardless of anything else that happens, the gravitational force always points downward. Right? The force due to a spring will always point either back towards equilibrium along the length of the spring, or I guess in either way, it points back towards equilibrium. So it might, the direction it will point will depend on whether it's stretched or compressed, but it's always towards equilibrium, regardless of anything else that's happening at the moment. Consider, on the other hand, friction. If I take and put a block on a flat surface and pull it with a string, then the free body diagram looks like this. Normal surface block, tension, I'm going to go with rope. Here's that gravitational force that always points downward. Right? So far, so good. Now, if I take that same block and start pulling it up an incline, let's try that again. Notice every force except the weight force has to change direction because the direction of the velocity has changed. And because the forces follow what's going on with the velocity, they're non-conservative. Okay. So notice, for our two conservative forces, we were able to define a potential energy for them. So I don't need to consider work due to conservative forces because I have potential energy terms that will take care of that for me. But when I have non-conservative forces, I do need to think about how much energy they add or remove from the system. So what does the work energy theorem tell me? That work equals the change in energy of the object. Okay. Well, if the object's energy is increasing, that means that the final energy will be bigger than the initial energy. So again, if energy is increasing, then final is bigger than initial, and whatever force that is adding energy, and work will be positive. If, on the other hand, the object is losing energy, then the final energy will be less than the initial energy, and that will make work negative, and that force will be taking energy. Okay, so now we have two definitions of work. We have work equals change in energy. We also have work equals FD cosine theta. So which one's valid? Both. there are two ways of determining the amount of work that is done on a system. You can look at its change in energy, or you can look at what the forces are doing. So how do you know which one to use? This is the really horrible answer. Look at the information you're given. If you're given information that leads to you being easily able to calculate work by force and distance, then by all means calculate it with force and distance. If, on the other hand, the information you're given leads to energy calculations, then you're going to need to use the work equals change in energy version. And oftentimes, to answer questions, you're going to have to use both definitions together. In the next part, we're going to be doing examples using the work energy theorem. Before we leave this part, we have one more thing to consider, and that is thinking about a roller coaster. So here we have a picture of a roller coaster, and you can see that here the initial hump of the roller coaster is taller than every single other spot on this roller coaster if you look at it. And not only that, you can kind of follow the path of the roller coaster because it starts here, it goes up, comes down, goes here. There must be something that gives it a boost of energy to come around and come around and loop back somehow. Where it exactly is, I'm not sure. But why do the humps get lower? The reason the humps get lower is because of friction. And friction removes energy from the roller coaster, which means that you have work being done by friction, taking energy away. So when I start at this height, I go down, I lose energy, and I come up, but because I've lost energy, I can't make it back to the same height. I can't go up as high as I started. That concludes this section, or this part, and in the last part of this unit, we're going to work examples involving the work energy theorem.